안녕하세요. 반도체 재료 및 소재 수업을 시작하겠습니다. Hello everyone. Let's start Semiconductor Materials and Devices course. My name is Young-Dal Jo from EECS. Let me use the laser pointer here. Okay, from EECS, School of Electrical Engineering and Computer Science. My email and a lab website. And this is the course website. Probably we won't have office hour for this semester. Instead, we can add the comments and questions into the JL website or EECS YouTube channel. Okay, so goal and textbook of this course. Firstly, golden rules of science and engineering. These are based on my experience and also the summary based on what I have read through various textbooks and some advisory books. First thing is always we need to specify the purpose whenever we start something. So it could be purpose of your device, purpose of your talk, purpose of your paper. So what is your purpose of taking this class? If we can answer that, then maybe you can learn better. The purpose of this course is given here later on. And also when you talk about the device, you do it based on the underlying mechanisms first here, and then phenomena. What is underlying mechanisms? The most common example could be like drift. Drift is the familiar word, with us. Something is moving around. In our case, electron is moving at a certain point to the other point due to the electric field. That is drift, and it's called as mechanism. And what is the phenomena? There comes current generation. When the electron is also accelerated during this drift motion, there comes light emission. And actually even below, even under the mechanism, there is something called principle. Okay. So the principle could be like a Coulomb interaction, for example. Coulomb interaction. Coulomb interaction, and those Coulomb interaction is mathematically formulated based on Maxwell equation, which you might have studied in electromagnetics course, but most of this class will somehow skip the principal part. Okay, we'll skip this part because we don't have enough time. So mostly we'll start from the mechanism first. Alright, and then say no to vague and negative expressions. So we make it clear and positive. Incorporate questions and comments of others. Questions matters a lot. Question matters. So basically, I consider question to be one of the most important approaches to study these device and material concepts. So whenever you have some unclear part and want to have some discussion on your ideas and thinking, then leave the comments. improve your previous thinking research with time? Yeah, surely we do. And we need to be detailed with time. Adapt to given research conditions and environment. So I mean, I don't have this one, I need this one, then I'll be great, I'll be perfect. No, such things don't happen when you try something new. There will be lots of the unexpected happenings, events. Then we just adapt to the given research. Given is always given, and we just accept, and we decide what to do in this condition. In that way, you can find the order instead of chaos. If we find the order, then things will look simple. Okay. So whenever we talk about device and materials, we talk about something related to the order instead of chaos. Oh, this device got this problem. This doesn't work. This is very different with principle. No, we personally, we talk about the order, what is going on, what is the principle, and then to solve some issues, then we consider some other chaotic points. Okay. So if we can remember some of the golden rules, then it will help. The purpose of this course is it provides a basis for understanding mechanisms and phenomena of semiconductor devices. And this is engineering-oriented introduction to the semiconductor materials and devices. But it is also designed to provide strong, intuitive foundations on the manipulation and acquisition of electronic information. You can discuss things based on mathematical formula, surely you can do. But before doing that, try your best to provide the intuitive picture. Okay? What could be going on based on some logical structures? Okay? That will help. And then we will somehow focus on electronic information rather than photonic information or like a sound information. I'm transporting my voice via sound now, and sound is called as phonons in science and engineering area, phonons, but we will mostly ignore that part. Semiconductor is mostly closely related with quantum mechanics, and its scale is nanometer. So many of the nanoscale devices are correlated. Okay. Textbook is the an introduction to semiconductor devices by Nima. And this is the reference, Physics of Semiconductor Devices. This is useful throughout many areas like electrical engineering, mechanical engineering, physics, and so on. So it is sort of the encyclopedia of semiconductor devices. Course schedule. We will start from crystal structure of solids. And actually, to understand better, we need to know some of the quantum mechanics. And the theory of solids are mostly based on quantum mechanics. And then semiconductor in equilibrium. So here it means equilibrium means the energy of the electron doesn't change much with time. Position of electrons don't change much with time. And then carrier transport. I mentioned the drift drift is the one of the transport phenomena, and excess carrier phenomena. And then there comes midterm exam. How to do this we'll discuss later. Okay. Then carrier transport and excess carrier phenomena, followed by p-n junction and metal semiconductor contact, and then metal semiconductor contact and MOS capacitor, and then MOSFET, and then optical devices. There might be buffering week because some of the coursework could be delayed, or we might need to discuss some additional contemporary topics, and then we will have the final exam. The grading, firstly, it is based on homework. There will be problem sets, possibly 5 or 6 problem sets will be assigned. The deadline is before the class on Wednesday of following week. So when you have homework problem set assigned today, for example, then you will submit the problem answer sheet like next Wednesday before the class. Can be submitted via GL Online or into a box in front of my office. Yeah, midterm and final exams will be there. Grading is based on homework problem, midterm, final, and there will be question points. Okay, and that question point will be assigned to some of the questions that are relevant and helpful to class teaching. Okay. Now always count the good questions on your name. All right. The brief history telling: electronics versus optoelectronics. We are somehow familiar with transistor concepts. Transistor is the device which can amplify the current or voltage. It was invented in 1947 in Bell Lab by some physicists. Usually they got Nobel Prize. And then by integrating some of the transistors, possibly together with capacitor and or resistor, it is called as integrated circuit. So IC. Yeah, another Nobel Prize was awarded for this topic. And then there comes MOSFET in 1960. This is actually very practical device which is being used for modern day electronics. So any of your CPU of your computer is based on MOSFET. So this is actually backbone of the computing nowadays, backbone of AI or machine learning, for example. It is invented by Kang Dae-won. Dr. Kang Dae-won is actually a Korean guy from Seoul National University Physics. He's actually my senior. So it's quite interesting, It's one of the most practical devices in modern day, It's invented by a Korean guy. Was invented by a Korean guy. For the optoelectronics, we are familiar with solar cells. Still, it is being, improved in terms of efficiency, right? School, actually, there's the institute somehow specified for this topic, solar cell. It's been a while actually. 1954. Around this time, actually, laser was also invented in 1950s. Then, in terms of semiconductor devices, semiconductor laser, showed up like 1962 by the famous physicist Hall. Surely, I mean, before the semiconductor laser, there comes the semiconductor LED, light emitting diode. Light emitting diode was commercialized in 1960s based on gallium arsenide phosphide. You can see in this calculator the red color display. These days this color is quite different with different colors like a blue, red, white, green, and so on. Those are all because of the following inventions, mostly from Japan. Those are explained here. Okay. All right. So. Many of these topics will be discussed later on. Repeated in this course. We all can note that this is actually Korean guy. Okay. And also the LED was originally red color, but these days blue, green, all different colors showed up. Blue LED was one of the most difficult to develop in old days. The inventor got the Nobel Prize. One of them was Dr. Amano. He's visiting our school quite often. He got the research institute here. So quite often we work together. Okay, in terms of LEDs, so x-axis is years, y-axis efficiency of LED, and this color of the lines indicate the color of LEDs. So originally from the 1960s, the red color showed up, and it is based on gallium arsenide materials. Within gallium arsenide, we put some additional, phosphorus into there, and we have the gallium arsenide phosphorus LED. And there comes some other materials like a gallium phosphide, zinc oxide, gallium arsenide phosphide doped with nitrogen, and aluminum gallium arsenide, and this slash means it has heterostructure. The meaning of heterostructure you will learn later on. And then aluminum indium gallium phosphide, and then aluminum indium gallium phosphide also used for different colors with higher efficiency. Actually, these days most of them are gone. Maybe this gallium arsenide based materials still survive, but most of other materials are already gone because it is all replaced by gallium nitride based materials. So around the 1990s, there comes the indium gallium nitride LED, developed by Japanese guys, especially personally from Nakamura. Then blue color is the most difficult one. Green color has the similar high energy like blue color, by changing some of the composition of the material, the blue color was changed into green color. Okay, so greenish color. Yellow also has the similar, energy. So they are very similar with each other. By adding red, green, blue, you can have white LED, right? By adding them all. So as we develop the different colors, then we could develop the white color. So the all different colors could be now generated. This UCSB, the University of California at Santa Barbara, now leading this area. But actually, the reason why they are leading is the old Japanese inventor moved into this school. So actually, Nakamura is there to lead this work. Anyway, to study those semiconductors, one of the most important concepts is band gap. And this star is explained here. The difference of energy of conductive electrons in conduction band and holes in valence band. The meaning of band, you will learn it later on. Okay. There's a band of conduction, there's a band of no conduction. And their separation is band gap. Something is vacant in between. That is called as band gap. And that band gap is changing with different material composition. Different material composition leads to different lattice constant. The concept of lattice constant, you will learn it in in later chapter. But basically, lattice constant means the distance between atoms constituting the solid crystal structures. You will repeat this concept again and again. But anyway, at least for now, different material has different band gap. And you can see that the x-axis is the lattice constant in the unit of angstrom. As we increase the lattice constant, the band gap tends to decrease. Okay. Aluminum nitride has lattice constant around 4 point something angstrom. It has very large band gap, like a 5 electron volt. Gallium nitride has band gap around 3.4 electron volt, and lattice constant is around here. And indium nitride, originally it was thought to be around 2 electron volt, but quite recently, it turns out to be much lower, like around 1 or even lower. And you can see many other materials. Traditionally, people studied silicon a lot, right? Silicon band gap is around 1 electron volt. Lattice constant around 5.5. Okay, some other very important semiconductor material is gallium arsenide over here. Gallium arsenide. The band gap is around 1.5 electron volt. Lattice constant is around 5.5. Okay. So silicon, gallium arsenide, and this gallium nitride, they are actually very useful materials. Okay. You will see them quite often. And also, the solid circle is called as direct gap material. Open circle called as indirect gap material. You will study these concepts pretty soon. So basic idea of photovoltaics, like solar cell. The meaning of photovoltaics is photons are turned into voltage. How can you generate voltage? It means positive charge and negative charge are separated in space. In this figure, actually, we are using wave picture of electrons. You will learn this later on, but some of you might be familiar with this, especially if you are from physics department. So just like photons, you can draw the figures based on energy and wave vector. Okay, and when you calculate those things for each materials, you can get the conduction band and valence band. Conduction band, you have electronic states. Okay, valence band, you have Hall states, and photon is coming incident. This photonic energy is replaced by electronic energy. So this field circle indicate electrons. Okay, open circle indicate holes. Okay, so originally electrons staying in valence band and excite into conduction band. It leaves some holes, the vacant electronic state. Electrons are vacant in this certain state, then we call them holes. Surely it will be studied again, so don't worry about it if you don't understand for now. But anyway, photons are replaced by electrons and holes, and then if they are separated in space, then it will generate the voltage. That's the concept of photovoltaics. So light is replaced by photocurrent or photovoltage. Also, you can consider the semiconductor lightings. This opposite concept. I mean, there's conduction band and valence band, and electrons are here, hole is here, and electrons going down to the lower energy band, and the energy separation by this conduction band and valence band, in other words, band gap, that energy is replaced by photon energy. That is idea of semiconductor lighting. And this is the idea of LED, light emitting diode, and then laser. Surely laser needs some other additional concepts like stimulated emission. But yeah, you will discuss later on, probably in the end of this course. The electron and holes are generated by applying external voltage in LED, and these are actually based on PN diodes. The PN diodes you will learn it later on. And this is the basic concept. The details will be studied in a separate chapter of this course. But basic idea is there's something called p-type material. The idea of p-type material means you will intentionally add some holes. Holes are positive charges. And the n-type material, you will intentionally add electrons. And so p-type material and n-type material, they are attached with each other. There comes interface in between, okay, and you turn on the external bias like this. So if the p-type material is connected into the positive bias, n-type material connected into the negative bias, then it is called as forward bias. Okay. And this solid line indicates the conduction band. Another solid line underneath is valence band, and their separation, band gap. So there's no energy state in between. Only the solid line has the electronic state, electrons. This solid line has the valence band. It is the valence band. It has the whole energy states. And then around the interface, you will have something called depletion region. Depletion region. The details will be studied repeatedly in this course. It's called depletion region. Okay. So in this depletion region, electron and hole, they can meet with each other, and we call it recombine. If there's a recombination between electron and holes, there is light emission. Okay. Then this p-type material and n-type material can, in case, include in the middle of intrinsic material. Intrinsic material is, it is not doped. I mean, p-type and n-type called as doped is named as doped material. It means semiconductor is mixed with some additional atoms to intentionally add some holes. Okay, you'll go through some detailed processes later on. And here in n-type material, you intentionally add electrons. Okay, in between you didn't add and you didn't dope any holes or electrons, then we call it intrinsic material. Okay, so now PIN diode will be formed under the external bias. Okay, your external bias. And we call it heterojunction. Okay, so this layer is heterojunction. So hetero means some different material. Junction meet in this area. Okay, so this is a little bit more detailed picture of Venn diagram. Okay, so heterojunctions, different band gaps, confined carriers. Confined means electron is somehow localized around here. So look at this, electrons are somehow localized here because it has lower band gap, lower energy state, and electrons prefer to be in lower energy state. Hole, in terms of hole, actually this is the lower energy state. Actually you will learn this concept again, but in terms of holes, the higher in y-axis indicates the higher position in y-axis indicates the lower hole state. So the holes will be localized, accumulated, or physically speaking confined in this area. And then electron holes, they are overlapping here. They can be combined to emit the light. So basically we are attach different materials, at least 2 different materials, sometimes 3 different materials, by inserting the heterojunction between P region and region of diode. The efficiency improves. And then there comes quantum health. There was active region here between P and end of the region, and you need to add very small area, like in quantum scale usually indicates that scale less than 10 nanometer. Then you need to consider quantum mechanics, because everything behave like wave in this small scale. Here everything means electrons and holes, you know. Electrons and holes behave like waves in this small scale, less than 10 nanometer. The reason we call it quantum is because now things are understood based on quantum mechanics or the wave properties of electrons. When things are confined within small well, they show wave-like behaviors. By using quantum wells, PI and diode work better, and this is the key idea for making better LEDs. So any of the modern day LEDs has this, you know, quantum confinement. Electrons are confined in quantum wells. Okay, so now one of the most important semiconductor material, silicon, is discussed in terms of energy wave vector diagram. Sometimes people call this energy momentum diagram because wave vector is proportional to momentum. Okay, momentum. Sometimes we call this as dispersion because energy momentum relationship was originally discussed for photon. In the case of photon, the energy K diagram is sometimes called a dispersion. Alright, anyway, if we draw the conduction band, there are many ups and downs. Goes up, goes down, goes down, goes up, goes down, goes up. It shows actually very complicated phenomena. But mostly what we care is around this lower energy point, because the energy of these electronic states are, you know, varying at different K positions, but eventually electrons will be accumulated in lower, you know, energy positions. Okay, and this local minimum of electronic energy is called as valley. So this is called as L valley, this is called as gamma valley, this is called as X valley, where you find the minimum energy of electronic state. We can do the same for the whole energy state or balance band. Okay, so for the balance band, there's a gamma valley here. There are many splitted bands, but we'll ignore for that part. But for now, you see that the lowest energy point of holes here and lowest energy point of electron is here, and their K point is different, and this corresponds to the band gap. Okay, and the K point is distinct, then we call it indirect band gap. Electron will be accumulated here, hole will be accumulated here, and only vertical in K-space, only vertical transitions are allowed in any materials where the momentum conservation. What it means is the most of case when there's electron hole recombination or electron transit into the lower energy state, then there comes light emission. Whenever it happens, it is vertical transition like this way, because the not only the energy but also the momentum should be preserved during this transition phenomena. Electron is now replaced by photon, and the energy and momentum should be conserved between them. So original electron momentum, let's say it is defined here. Momentum is proportional to the K wave vector. And then what's the momentum of light? It's almost zero actually, because you know the light, the photons doesn't have the mass. Photon doesn't have the mass, so its momentum is actually very low. So when electron is replaced by photons, it mostly happens around here, not like this. So indirect gap semiconductor materials like silicon are not optically active. So silicon is optically less active. On the other hand, in the case of gallium arsenide, if we draw down the band structures, the lowest point here for the electrons, lowest point here for the holes, they match at the same K point. It is called as direct band gap. Optical transition is now very strong. It is direct band gap material. Gallium arsenide, gallium nitride, indium arsenide, they are all direct gap material. They are optically active. So what do we need for device R&D? Previously, we surveyed some of the important concepts of this course, and those concepts will be studied from different courses like quantum mechanics. Most important thing is Schrödinger equation. Okay, this is the something like Newton's equation of motions, interpreted in terms of quantum mechanics. And based on that, you will learn the electronic structure, wave functions, and it is closely correlated with the optical properties. Electromagnetism should be studied based on Maxwell's equations. Optical field, waveguides, propagation, transport, those things should be studied here. And also the kinetic theory, it is actually studied based on the statistical mechanics. Statistical mechanics. One of the important courses in physics department, and also it is actually studied in mechanical engineering department. There comes Boltzmann equation. It is related with the carrier distribution functions. It will be studied in this course too. Potential profiles, scattering mechanisms. Scattering mechanisms is very important these days. But it is a little bit complicated, so mostly ignored in this course. And then current densities. So in some sense, these are all physics concepts actually. So semiconductor device and materials are actually closely related with physics. You don't need to get scared by these physics terms, because actually it is well established. If you check out some other YouTube videos, you get lots of good lectures about these physics concepts. So don't be afraid. It's pretty straightforward these days. I know one of the best schools always have the physics courses, even in electrical engineering and mechanical engineering courses, and these days we don't separate them that much. Electrical engineering, physics, and mechanical engineering, they are now mixing together. They are fused and integrated these days, so they are actually studied all together. And then there's real electrical engineering concepts: IV, current voltage; CV, capacitance voltage curves; and optical output, current output, efficiencies. These are the electrical engineering concepts. And also the chemistry. Material growth issues are closely related with the chemistry. Still, it is being studied a lot. Interface issues, defect issues, growth of epi layers, especially these days. People care about the monolayer structures in 2D. So it matters a lot these days too. So they are actually all mixed together, so at least you should know these concepts. Alright, so some of the topics to be discussed more are closely related with what is going on these days. So first thing we need to know is the evolution of transistor, and sometimes it is epitomized in terms of Moore's law, named as Moore's law, to explain things in simple terms. So basic idea is this y-axis is the number of transistors within a chip. What's the meaning of chip? It is like a 2.5 inch wafer. Within this scale, you put lots of transistor into there. This is year 1971, 2018, and the number of transistors within the chip, or we can say density, increasing with time. Okay, so there was certain slope, and that slope was like sometimes 1.5 or 2 times, like every 2 years, and that's called as Moore's law, and it doesn't work anymore. Look at this, it is already saturated and it doesn't improve anymore because we almost there around the limit. Transistors are already too small, so it ended. Moore's law ended already. So you are in that era. So people discuss, then what should he do? What could be the alternative? How can he get it better? So future of computer chips. Around 2015 and later on, people discussed these issues again and again. These days, because of the single transistor in the chip is now limited, we connect them. So cloud computing, okay? Or sometimes we replace materials. For example, silicon can be replaced by some other materials. For example, graphene, whose electronic speed is much higher than silicon. So graphene transistor, for example, could be pursued, and also quantum computation. We just change the algorithm, and then the related contemporary topics are listed here. Semiconductor devices, CMOS and related chips, LEDs. Originally, laser was used to amplify the light, but these days you can also amplify the sound or the heat carriers. It is called a furnace. And electronic diode rectify the current flow direction, right? And there comes new concept like a thermal diode. The heat flow will be rectified. That is very new concept. And there's also quantum cascade laser. in new materials, especially van der Waals heterostructures. The layer by layer, they got the van der Waals interaction in between. Something called like a graphene, photon nitride, black phosphorus, and TMD schist, transition metal, the chalcogenide. Strain, phonon strain means the lattice structure is distorted. It's found very often in semiconductor materials, and phonons and heat. These are related concepts for heat transport, and then integration among them. Those are contemporary topics. And, we will ignore most of these topics for now, for this class. And if you're interested in the transistor concepts, then you can report to this website, okay? And this AIM photonics, so I'm actually interested in the integrating electronics with photonics, okay? Because the electronic information and photonic information, one of the most important topics we need to discuss first is their speed. And the electronic speed is much lower than photonic speed, photons. So when you want to transfer your information from certain point to the other point, if you use photons, then it will be faster. So in the concepts, things needs to be integrated between electronics and photonics. And these are actually part of the concepts only in terms of electronic part, and new transistor concepts, mobile materials, nanowire, those things considered. And also, instead of silicon, people are using some other materials like carbon nanotubes, MOSE2, molybdenum sulfide, okay, for transistors. And also in terms of heat transport, this transition metal chalcogenide materials could have certain form of quantum wells and multiple layers. Then you can control also the thermal transport. This is actually my work. Another concept is, okay, transistor efficiency is now saturated. What should he do? Surely, you can change the materials within, some other materials like a TMD schist, graphenes, and so on. But things are not, going very well. It didn't work very well. Graphene transistor didn't work very well. TMD schist now is not stable enough. There were many issues. And another approach is, even with the same material, if we remove the heat, more efficiently, then your device will survive longer and you work faster. So the for example, this figure is very famous one. Carrier drift velocity versus electric field. As you increase the electric field, carrier drift velocity increases, and their slope is called as mobility. You'll learn this later on. Mobility. And then mobility is fixed for the different materials, but look at this. Carrier drift velocity is not increasing anymore, it's easily saturated. For any material, it always shows the saturation behavior. It's because of electron phonon scattering. phonon is the lattice vibration. I mean, your atoms are not fixed, it is just moving around. That is named as phonons. So if we remove these phonons, then our electron phonon scattering will be reduced. Then your electrons will be moving faster. So, in other words, you can remove the heat, then electrons can move faster. These heat carriers are atomic vibrations. So how can you manipulate atomic vibrations? That is another issue. So in terms of that heat and phononic studies, originally I studied the optoelectronic semiconductor materials, but these days many of the problems are already solved very well, except the heat and phonon issues. So I'm mostly working on those issues, unsolved issues. And this figure shows the sound frequency. Sound also got their own frequency range, 1 hertz, 1 terahertz. For different frequencies, got related topics like diode concepts showed up. And this 1 kilohertz is the sound frequency. The sound is somehow manipulative. It worked very well based on these device concepts. And then there comes the ultrasound imaging, like medical imaging is very successful, and it is based on phonon manipulation. And there comes something new, like phononic crystals, and also our mobile communication uses the some filters like soft filters, and Bow filters. Those are actually all phononic devices. It is being used in your cell phone. Actually, they are utilizing around gigahertz range frequencies, and also 1 terahertz range. It is extremely hard, and it's a new area. It controls the heat, because the heat is transferred based on these phonons around 1 terahertz frequencies. There comes new concepts like this. So these are new, and it could be studied only after you understand those topics of these courses. So we won't deal with these concepts, but we will study it rather than these contemporary topics, but the basic topics like PN junctions, transport, and MOSFET in this course. Okay, that's it for this class in terms of introduction.